All right, so let's go ahead and interpret this map of intercepted solar radiation. Once again, let's look at what we found in our descriptions. So if we go ahead and look at our summary, we found that around the equator, we have moderate insolation and not the highest the way one would predict. And that we have the rainforest, which we know that with rain means clouds. Okay, and then between 20 and 35 degrees north and 20 to 35 degrees south, we see the highest amount of insolation, intercepted radiation, caught at the Earth's surface. And hence the world's largest deserts are there. And once again, we see the high latitudes as we move toward the North Pole and the South Pole. Intercepted solar radiation, insolation is decreasing. And then we compared in general the northern hemisphere from the southern hemisphere, and sure enough, we found that these generalizations could be made, and they're non-arguable statements of watts per square meter reached at the Earth's surface. So, as we ponder these ideas, let's think about where that takes us as far as the interpretations we want to make. So, I have a great animation to show you that I think will really help with understanding the adiabatic heating and adiabatic cooling that we see happening around our equator. All right, so if we look at what's happening here, clear these animations, we know that we have extra heat along our equator. Well, that extra heat along our equator makes the Earth itself warm the air that it comes into contact with. This warm air, being less dense than its surroundings, rises. And the further we go from the center of the Earth, the weaker the gravitational field, the less molecules in the higher atmosphere, and hence, with that pressure decrease, the volume of these air parcels can increase. So we see this volume expanding in these air parcels, which allows the air temperature in that parcel to cool. With that cooling, we see condensation, a switch from a gas to a liquid, cloud development, rains, and the rainforest. We call this zone the intertropical convergence. So within the tropics, and you can see right here that this air, sure enough, is coming together. It is converging. So let's get back to that. So this ITCZ, this intertropical convergence zone, not only is dynamically lifting the air, but it's the initial warm air that creates that relationship between pressure, volume, and temperature that we call adiabatic cooling. So as this cool air migrates to the north and to the south, it's more dense than its surroundings now. And so as it sinks toward the Earth's surface, sure enough, it collides with the Earth's surface, feeding back toward the equator. And that collision is what's driving our westerly winds dynamically. So when we have sinking air, we have a high pressure system overhead, and you can see that roughly between 20 and 35 degrees north and south, we have sinking air. These are called the subtropical high pressure zones, and sure enough, this is the location where we see our world's largest deserts and the world's greatest amount of intercepted solar radiation. Right? And so with this understanding of Hadley cell development, we can move on into coming back to the two other explanations we've been looking at when it comes to this map of insolation. And what we can see here, sure enough, is that on this oblate spheroid, this round Earth of ours, right, when the radiation is not vertical, but instead is really direct, we can see that this radiation is more intense. But as we go up into the higher latitudes, radiation is spread over more area because of this diffuse this low angle that creates this diffuse radiation near the poles. In addition, one of the really fun things to notice is if we were to shut off the southern hemisphere, not look at it for a minute, wow, would we see that the northern hemisphere is dominated by land. Land has a low specific heat capacity, as you know from what we've been studying. And that creates the ability to heat up quickly and cool down quickly and create more extreme conditions. Hence, our highest amounts of insolation in the world are in the northern hemisphere. While the water hemisphere, the southern hemisphere, creates a much more moderate conditions. And so with these descriptions we came up with, we can now summarize our conclusions. And that along the equator, roughly in that intertropical convergence zone, right here, the ITCZ, we have constant cloud cover all year long because that warm air, as it rises, the pressures decrease, allowing volumes to increase and temperatures to drop. Condensation occurs, cloud cover, and all due to this adiabatic cooling. Well, adiabatic means without exchange of energy with its surroundings. So it's a volume change that's causing this temperature change. And then we saw at 20 to 35 degrees north and south of the equator, we see that that sinking air all year long creates no cloud cover, permitting insolation to be able to reach the Earth's surface all year long. That sinking air, because it's cold and more dense, that creates a pressure that increases. As pressures increase closer to the Earth's surface, that allows volumes to decrease. So we see that air is compressing. And hence, with no exchange of energy with its surroundings, that causes that air parcel that's sinking to heat up adiabatically. Adiabatic heating is creating the sinking air, which creates no cloud cover and allows the sun to reach the Earth's surface all year long. And then at the higher latitudes, we see that as we move up into this oblate spheroid, the angle of the sun's rays is over greater amounts of area, and so it's less intense intercepted solar radiation at the higher latitudes versus very direct radiation where the subsolar point is vertical at the lower latitudes or low angle. And then last but not least, we know that the northern hemisphere is the land hemisphere, dominated by land masses, while the southern hemisphere is dominated by water. And as you know, water is the great moderator due to its high specific heat capacity. It takes a long time to heat up and a long time to cool down, but that ability to store energy, latent heat energy, and release that energy moderates conditions so that the northern hemisphere is extreme while the southern hemisphere is more moderate. So I hope that what you'll do now is go ahead and recreate this all on your own with your own scratch paper and be able to explain it to someone else, because this is going to take us into a even greater understanding of general atmospheric processes.